for everyone for showing up. Today we have William, who will be telling us about spectral sequences.
Yes, thank you everybody for coming. Today we're doing stuff that's a little more algebraic than normal. Last week we were talking about transversality of maps of smooth manifolds and felt a little out of place, and now I want to get into something that's a little more rigid and algebraic, feel more cozy and at home. So we're talking about spectral sequences today. So like a bit of historical context, there's like some history folklore around this. Jean Leray from France, he was captured by the Nazis, and he was in an Austrian prisoner of war camp from 1940 to 1945. And his main research up to that point was about partial differential equations. And so he thought that, you know, if my captors find out that I'm like a good analyst and I can solve these types of equations, they might like adopt me into the war effort and make me, you know, plot out trajectories of missiles or whatever. So what he decided to do was invent sheaves and sheaf cohomology, and he constructed a spectral sequence for computing sheaf cohomology. You know, maybe not in so many words, you know, he definitely laid the foundations for all of these ideas, and was sort of the inspiration for this idea of sheaves that Grothendieck kind of ran with, and also Serre was really big on sheaf theory. So Serre was he knew a lot about Laray's work, and he thought, okay, this idea of the spectral sequence, maybe we can adapt this to a different context, specifically a fiber bundle, or slightly more general, the context of a fibration. So that's where I'm going to start, because maybe you've heard of fibration or fiber bundles before, but the fibrations are kind of a more general class. If your fiber bundle's nice, then it's a fibration automatically, but there's lots of fibrations that aren't fiber bundles. But they still behave up to homotopy in ways that are like fiber bundles. In particular, nice enough fiber bundles have something called the homotopy lifting property, which I am describing for you right now. So let's start with the continuous function, pi. And we're going to want to say what it means to be a fibration. So for any continuous space X, you can say what it means to have the homotopy lifting property with respect to that space if, well, a bunch of formal symbols. What do these formal symbols mean? Means if you choose any initial map of X into the total space, and if you look at its projection in the base space, B, and then apply some homotopy to that downstairs, that's H, then there is some lift of that homotopy upstairs that, you know, is a homotopy that starts at a particular G, our initial value, and traces out a homotopy upstairs that covers the homotopy that we started with. So, you know, if you start with any initial value upstairs, take a homotopy of its projection downstairs, then there's actually a full homotopy lift, a lift of that homotopy upstairs that projects down to the whole thing. So you call this the homotopy lifting property with respect to X. And it's not necessarily unique. So here's a point. So for nice enough fiber bundles, yeah, okay, no. I'll write down the rest of the definition. So I haven't really defined it yet. Let's not go crazy. So a Hurewicz fibration this is a map pi from some space E to some B. By the way, I'm using these letters like in fiber bundle theory. B is going to be like base space, E is like entire space, like we were talking about the other day. So you should think about E as being like sort of fibered over B in a way that I'm going to describe. So a Hurewicz fibration is just a map that has homotopy lifting property for all X. Okay, and so some examples of this are sufficiently nice fiber bundles. This is sort of like the big nice property about fiber bundles and covering spaces that we really like is that they have this homotopy lifting property, at least as long as they're CW complexes. It's going to have to be a restriction that we're going to make a lot today is to the category of CW complexes, because some of this stuff is pathological and it doesn't always hold unless something's a CW complex. So this is a Hurewicz fibration is for all x. So as you can expect, that's probably, we're trying to generalize fiber bundles. This is maybe too much to ask for. So a weakening of this is a Serre fibration. This has the homotopy lifting property for x equals dn, just disks. So that's all you require for a Serre fibration. So from this, it actually follows, in fact, you have homotopy lifting property for CW complexes as well. So Serre fibration is kind of a more convenient tool to work with because it's designed for, assuming that everything works for CW complexes, and that's often all that you need for these types of constructions. But it turns out if, a Serre fibration of CW complexes. So if E and B are CW complexes, then it actually is a Hurewicz fibration. So when you're restricting to the class of CW complexes, these two notions are actually indistinguishable. And for all our examples today, that's where we're going to be. So we're not going to have to make a distinguishing between these anymore. I just wanted to point out that there is a difference between these two classes of objects. This one's much, much more restrictive. But if you're only working with CW complexes anyway, any one of these gives you one of these as well. So that's pretty cool. Yeah, we are not going to be doing like check cohomology. Everything is detectable with ordinary cohomology. Yes. Okay. Yep. And then, so kind of one of the big nice things that we love, right? I said that a covering space in fiber bundles, or at least if they're sufficiently nice, they have this homotopy lifting property. We use that homotopy lifting property in order to get us the long exact sequence of homotopy groups. So here's a fact, a lemma or an exercise. What am I saying? So if pi is a Serre fibration, and I'm probably going to stop writing Serre, and I'm probably going to stop mentioning that everything's a CW complex, and we're just going to take that as given. So if pi is a fibration, there is a long exact sequence in homotopy groups. So if we have the homotopy group of, let's write down spaces so we can see what's happening. And we're going to take base point to be B naught. We're going to take these as a pointed map so that we can do homotopy theory. Okay? So if we take the homotopy groups of the base space pointed at B naught, or rather let's take E, one in the bid. So we have our projection. Yeah, this is going to run into problems. Let's say F. Sorry, everybody. So I need pi for the homotopy groups. It's going to look weird to have an extra pi flying around. I'm going to have to switch to F. So we have the push forward of F to the homotopy groups of the base space. We can consider the fiber F inverse of the base point B naught. And F inverse of the base point B naught in particular is going to contain E naught, because E naught goes to the base point by definition. And so we're going to point the fiber by just taking E naught as well, so pointed by E naught. So we also have pi n of the fiber that we include into E by some map called I. And then we have a strange boundary map into pi n minus 1 of the fiber. And then, Okay, so this is a primary computational tool for figuring out homotopy groups of fibrations. And we're going to be using it over and over and over and over again, or at least a few times. And the way that you derive this, it's not so hard. You start with the long exact sequence of the pair, pi n EF. And then you use the homotopy lifting property to show that, in fact, that precisely agrees with the homotopy of B. It's a really clever thing. You should go do it as an exercise. E comma F is the pair space of E and a subspace F, the fiber. And so the relative homotopy group, remember this was just maps from the n-dimensional disk into E, whose boundary lands in F. And so this boundary map is actually, once you make this identification, you're just taking that boundary, you're taking the map of the n sphere restricted to the n-1 sphere, and that gives you an element in a map from the n sphere into F, because the boundary is in F. Yeah? Yeah. So that's how it works. Yeah.
Yeah, I think you said n sphere for the last one.
Yeah. Okay. So we love fibrations because of this. And here's a really interesting other fact. So given any function continuous from E to B, so we can replace it with a fibration. Or at least it's going to be a fibration onto the path components of B that F actually hits. So in fact, let's make the assumption if F is surjective on pi 0, then we can turn it into a fibration. The point being, because like a fibration needs to be surjective, you can go and check by applying the homotopy lifting property to maps of points into your space. You can see that a fibration actually has to be surjective. So if this map doesn't see some path component of B, this construction I'm about to write down, it's never going to see that path component of B. So in order for this to work, we're going to need to have this surjection on path components. So how does it work? So let's let PF, this is going to be a set of triples. One of them is going to be an element of E. One of them is going to be a path in B. The other one is going to be an element of B. So where am I saying this is an E cross paths in B? This is notation for function space, continuous functions from the interval into B, cross B itself, with the property that gamma is a path from F of E to B. So what the heck? So here's your E, here's your E, here's your B, here's your B, here's your F of E, here's your F, and then gamma is going like this. So for a fixed E, basically every B that lives in the path component of F of E gets like an entire family of lines going to it. So this is like a huge, huge, huge expansion of our space at E, is this set of paths. So we have functions, convenient functions. We have an embedding of E into path space of E, of F, by taking E to the triple that just sits constantly at E. Constantly at F of E. So gamma sub F of E is just the constant path at F of E. So every element of E gives you a pretty trivial triple. And we also get a map going the other way by taking this triple E gamma B and just spitting out the E coordinate, start of the path in E. So this is a homotopy equivalence pair. Okay, so if you embed E into your path space and then project back to E, you get the identity. Okay, well, what about the other way around? If you take an arbitrary thing, right? So this arbitrary thing being, right, a point and a path to B, and yeah, and you just take the starting point and then you go like this. Well, now you've definitely done something totally different. Instead of taking this path over to this random B, you've decided to just do nothing. But this composition of starting here and ending here, those two are actually homotopic as maps, because you have this sort of slurping spaghetti effect where you can just do less and less and less of the path until your composition from, I'll get to you right after the sentence, So your composition going from here and then back is actually homotopic to what you started with, the full path.
Sorry,
Yeah.
I missed the relation between I0E and I0B. You're saying that they equals reject?
Yeah, so like every path and component of B has to be hit by some element of E. Yeah. And so, okay, so here we have a homotopy equivalence with this weird path space that we made. And moreover, this is an exercise for you, of course, that we also have a function pf to the base space, which I'll call f bar, and that takes a triple, and it projects it onto the other spatial coordinate, b. So, right, instead of projecting onto E over here, you have your weird E and your path to some B, and you just pick out your B. Okay, so it turns out that this is a fibration. So by adding in all of these paths, if you go do this as an exercise, by adding in all of these paths, we actually like put in coordinates that allow us to construct a homotopy lift pretty much canonically. So this is the fibrant replacement, okay? So like we started with an F, and we had a map to B, and it has some surjectivity on path components. And now we can replace our total space up to homotopy equivalence by this PF, and you get a new F bar so that this is a fibration. Okay? And this is like a functorial thing as well. So if you have like a map from this pair to some other pair, then you're going to get a map from this path space to that path space, and everything's going to compute. Okay. So why did I want to do this? Is this board like visible from the camera? Is that good, or should I go back? Oh, I just have to write down one thing. If I can remember what that was. Yeah. So the point of doing this is that, like I said, when we have a fibration, we get this long exact sequence. If we have just some arbitrary function, given any function, this is just giving us a family of maps, right, between the homotopy groups. So pi n to pi n, and there's no connection between them. But by turning this map into a fibration, we've sort of produced the missing groups that we would have in a long exact sequence by making a space who actually fills in that gap. So the definition, this is one definition of a homotopy fiber. So if you just have some function, the fibers, they can be any random stuff. But if you have a fibration, the homotopy fiber, I forgot to mention this. Okay, I'll say it like this. So the homotopy fiber of a map F from E to B at the base point B0 is, right, so what you do is you take the path space for F, and your F bar to B, and then you take F bar inverse of B0. So this is called the homotopy fiber. And I'll put the base point in subscript and the map F like that. And most of the time I won't put the subscript in because it's already hard to read. So we replace our F with a fibration and then take the fiber of that fibration. And so the fact that I forgot to write down before I went off on this tangent, so if x, let's say like this, f, x, and x prime are connected by a path in B, then, if f is a fibration, then the fibers over them have the same homotopy type. So there's a homotopy equivalence of F inverse X, F inverse X prime. Homotopy equivalence. Yeah, so that's really important. I'm embarrassed that I forgot to say this. So if you have a fibration, especially a Hurewicz fibration, but everything for us is CW, so it doesn't make a difference, then using the homotopy lifting property, applied to like this path where you start with the identity function for the fiber over x, project to x, take the path, and then lift that homotopy. That'll give you a map from the fiber here to the fiber here, so that if you go the other way around, that gives you the homotopy inverse going the other way. So these two fibers are homotopy equivalent. And so, right, starting with any function, by replacing our function with a fibration, we've sort of produced like the canonical homotopy type for being a fiber in the fibration given by this map F. So like you can have different homotopy types, like you can change the homotopy type of the fiber in a fibration. I haven't given an example, but here's a fibration. Take the right angle triangle and then project onto the bottom line. So that's not a fiber bundle because the paths aren't constant. This one's a point and this one's a line, but you still get a homotopy lifting property for this projection. And you can see, in fact, yes, all the fibers are homotopy equivalent. Okay. Well, that was a lot. So that's what I wanted to say in terms of just like the background on homotopy stuff and fibrations. So I should stop to ask for questions if people want clarification on that, because it was sort of a lot. And they might just be bored. So it's good to have a palate cleanse before trying to do something new.
I think you had already said it earlier, but or like alluded to it earlier, but as an example of fiber bundle, just in a fibration.
Yeah, good question. I checked that out right before I came here. I didn't look into the details, but like the idea is that your base space is so bad that it doesn't have the property that, like your base space is contractible, but you can still find a non-trivial bundle over it.
Okay.
Which is like if you have a contractible CW complex, every bundle over that is trivial. But like this guy comes up with this example over a contractible space that's not a CW complex, and he produces a principal bundle that like doesn't have a section.
That isn't trivial over a contractible.
Yeah. So what is the space is like you take two copies of R, say like R1 and R2, and then you do like the point R in here, 1 is identified with the point R2 in here if R is greater than 0. So basically, yeah. So you identify the positive ones, but then you have 2 zeros, and you don't do anything to the other ones.
Oh, okay.
So this is like, it's like the line, the line with 2 origins.
I was thinking of the first one,
Yeah. What were you thinking of?
Okay, first one as an example of like the real line with two origins.
Yes.
It's kind of like super pathological.
Exactly. Yeah. This is like you just do half of the construction, leave the other end open. And so this is yeah. If you had like identified the 2 points together, then you would just have 3 line segments. So like by breaking it like this, he's able to find a bundle that it's a principal bundle with no section, but like this is still a contractible space. So there's stupid stuff you can do like that. So we're just going to do CW complexes and not have questions like that. Yes. Is that your question?
Oh, I was just thinking about that. That's contractible, right? That's,
Yeah. Pretty sure.
The question I have is this. How do you pronounce this?
The homotopy fiber.
The homotopy fiber.
HOFIB, yeah.
Over that is just the F bar inverse of P naught.
Yeah. So to make the homotopy fiber of a map, you apply this fibrant replacement construction, and then take the fiber of that map. So the F bar. So you inflate E to make it an actual fibration, and then you take all of the stuff that this bigger fibration sends to your base point B. So I think that's going to contain like your actual fiber because you have this like fiber preserving embedding. Actually, no, this isn't fiber preserving. Yeah, just take back what I said. Yeah, so you make your E better, and then you take the fiber of that fibration.
I don't get that very last part, the fiber.
Yeah, so like the point was you have this arbitrary F,
Yeah.
and now you've made a new F that is a fibration.
Yes.
And so like whatever if you have a base point here and you want the homotopy fiber of F, that's just the fiber of F bar. You make the fibration and then take the fiber. Because once you have a fibration, as long as like the fiber is the same homotopy type over the whole path component. And so this is like, now you've made taking the fiber well-defined up to homotopy. So here, like your fibers are random stuff, but making it a fibration, whatever thing you choose in that path component, you take its fiber, you get like a well-defined homotopy type. That's the idea. Okay, just some technical stuff that I probably didn't have to talk about at all. Okay. So now we're going to change gear and talk about what is a spectral sequence. Also, you can tell me what time it is? I don't think that clock works. Okay, maybe it does work. Okay. Yeah. Okay, so on that note, the Serre spectral sequence this is something that applies to fibrations. Serre fibrations particularly. Sequence. So here's the statement. I'm just going to make a scary statement and then explain what it means for like half an hour or so. So let F E be. Now I'm going to let F just be the fiber over the base point, be a fibration, and I mean Serre fibration, but okay, of CW complexes, so it doesn't really matter. Actually, I think if you look in Hatcher, it doesn't have to be CW complexes. B just has to be path connected. And you prove it for CW complexes as a special case. So I will specify Serre fibration. Probably some other nice properties about B. Then, if the fundamental group of B, so by the homotopy lifting property, what's going to happen is that the fundamental group of B, if you go around a loop, you're going to act on the fiber by some map. Maybe I really want a Hurewicz fibration. Yeah, so if you go around a loop in the base point, that fiber, if you start at the homotopy, sorry, if you start at the identity, project, go around the loop, and then lift that whole homotopy, you're going to get a map from the fiber to itself. That's a homotopy equivalence. And so pi1b gets a map to like the self-homotopy equivalences of F, and so it acts on all of the homotopy functors that you can apply to F. So in particular, pi1b can act on the cohomology of F. So if pi1b acts trivially on the cohomology of F, then here's scary words. There is a first quadrant spectral sequence and I'll write it up here so that the E2 term of the spectral sequence is just the cohomology of the base space with coefficients in the fiber, and it converges to the cohomology of the total space. So now I'm going to take red chalk and I'm going to highlight all of the words that I haven't even made an attempt to explain yet. And so that's what we're going to talk about as we go. So first of all, what is a spectral sequence? What makes it a first quadrant spectral sequence? What is the E2 term of a spectral sequence? What does it mean for a spectral sequence to converge to something? So all of these are things that are sort of scary the first time you see it. So I'm going to try to walk through it, hopefully not too slow, because I do want to get to the examples. And also, how do you make them? So that's what I'm going to talk about the least, is how to actually produce a spectral sequence. It's a little dry, and that's not really the point of the talk, even though I've talked about a bunch of dry stuff already. That's neither here nor there. Okay. So what is a spectral sequence? This is kind of when the actual talk is starting. All of that was sort of a big preliminary. Let's fix a ring. And let's say that it has 1 in it. Good. So I'm going to write over here because it's going to be a big definition. spectral sequence over this ring R. And for us, R is almost always, I think it is always going to be the integers, is a family. So there's going to be one for each non-negative integer, sorry, positive integer. And these are bigraded R modules. Bigraded just means that, okay, instead of just being graded by one parameter, now we have two parameters. So the total thing is just a big direct sum over two parameters instead of just one thing. Okay, so bigraded shouldn't be the scary part in this definition. So we start with a family of bigraded R modules, and there's a very mysterious way of getting from one page to the next. And we call them pages, by the way. We call these pages. And we have R module morphisms called dr, and for a given bigrading PQ, so we're going to say we start at the thing in position PQ, and what we're going to do is go write P steps down Q minus 1 steps. So we're going to end up ER P plus R, 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 and then Q minus R plus 1. So this is very weird indexing, which will start to reveal itself. It gets longer and longer and longer as the pages go on. And we have the properties. First, this is a differential in the sense of like chain complexes. So if you apply dr in succession, you get 0. And the second should be that when you take the homology of this chain complex, right, so for people maybe don't remember, this means that the image of the differential, anything that is in the image of the differential is automatically in the kernel of the next part of the differential coming out of the thing. And so you can take this quotient group, that's the homology of the chain complex, and being a spectral sequence is saying that this is giving you the next page of the chain complex. So I'll draw a picture so that's a little easier to understand, because right now it's just symbols. The idea of a spectral sequence, the whole sort of philosophy, is that it's an iterative homology process. So I meant to say that before I even wrote anything down, so I'm saying it now. So the idea is that you have something homological you want to compute, and it may be very difficult to try to do it all at once, but if you can set up a spectral sequence that starts at something you understand, like, for example, in the Serre spectral sequence, we're trying to start at something that's related to the base space and the fiber. Maybe we already know everything about those spaces, and we try to compute the thing about the total space, the thing that we're aiming at, by this iterative sequence of going from page to page to page. You have this weird homology process given to you by these differentials. So like here's what a page would look like. I put my P on the horizontal axis because it's associated to the base space in the Serre spectral sequence, and Q is associated to the fiber. And so you'd have something like on the ER page, you'd have something over here in position PQ. And then down way over here, you'd have P plus R, Q minus R plus 1. There's a function, a morphism between these called dr. And there's another one coming out also called dr. And there's another one coming in also called dr. And each of these drs have images and kernels. And then on the next page, you go ka-chunk and do a homology process. And then the ER plus 1 at position PQ is the kernel of this guy, modulo the image of this guy. Yes?
Homology of dr will be dr plus 1.
Yeah. No, of course. That's like the most important thing, is that it's the next thing. Yes. That was just a brain fart. Okay. Any other good corrections? Yeah, so like I said, the dr differential, it goes right by R, and it goes down by r minus 1. So that helps you to remember how the degrees work. Okay, so to a remark. So for any element that's on the ER page, that's just in one of these modules. So there's two ways for it to not really make it to the next page. So the first is if it's not even in the kernel of the differential. So if the differential doesn't even vanish on your element, it doesn't even represent the class on the next page. It kind of just evaporates. It sort of gets filtered out of the process. The other way that you cannot really make it is if your differential dr sends you to 0, but you're in the image of the other dr. Something comes in and knocks you out. Okay, so if you want to actually represent something non-zero on the next page, you have to go to 0 here, and you have to dodge this error. So yes. I wanted to emphasize this for some reason. So not in kernel. So you kind of disappear. And if you are in the image of the differential, then it's like you got annihilated. So it's kind of two different ways that you don't make it. Yes? Yeah, so the idea is for a fixed point, you have all of these differentials kind of coming into you and going out of you on each page. And the whole spectral sequence is processing around you, and you're getting related to different rows and columns, because if you look at the slope of dr, if you go one longer, the slope actually goes a little bit deeper, and one more, it's a little bit deeper. So you're not always relating elements that are on the same row or column or whatever. You have this weird interplay between all of the different parts of the pages. And it's this very mysterious process that gradually computes things that you want. Okay, now, so this goes towards some limiting value. And so the idea is that at the next page, it's always like a quotient of the kernel. So if you have something that's just in every kernel, that the differential sends it to 0 forever, such a thing is called a permanent cycle. And sort of the set of all permanent cycles, you call that the E infinity page. So I'm going to be very rough with this just because we're not going to need to care about this. And I'd rather spend more time on more interesting stuff. So E, this is going to be the set of permanent cycles. So this is the set of elements that always represent cohomology classes forever. It might be 0. You might get hit by some image at some point, but you're still a permanent cycle if you're 0. Right? That's the only thing that you know for sure is always going to be a permanent cycle. And so this is what the spectral sequence is slowly computing. And that doesn't mean, and so let's say that it abuts. So ER abuts. If for all PQ, these values stabilize at some point. So if all PQ, ER PQ is isomorphic to E, so exists in R naught. For all PQ, like this, for R bigger than R naught, right? So for a lot of spectral sequences, it's not actually like a genuine limit. It sort of just hits something and then stops changing after that point. So for example, here's a good class of spectral sequences that always abut, and they're called first quadrant spectral sequences. So I'm going to get that word out of the way. So E is first quadrant. If basically it lives in the first quadrant, right? So out there is all the dead zone. The only thing interesting happens in here. So if E RPQ is 0 unless they're both non-negative. So this is what we mean by a spectral sequence. If by inspection the Serre spectral sequence is first quadrant because there are no ordinary cohomology groups in negative degrees. So these abut. So our convergence stuff behavior is never going to be complicated. We're just always going to know that for each point, there's some page where that value is frozen in time. Nothing's ever going to change it forever. And it's easy to see why these abut, because if for any point, I guess I should do it over here, right? For any point PQ, there's some R large enough so that any differential coming out of it lands in the dead zone out here, and any differential coming into it comes from the dead zone. So as long as both of the differentials coming in and out are 0, that means that doing homology takes nothing, because the kernel is everything and the image is nothing. So once the differentials are always 0, homology is like a stable process. Doing well. Okay, so now I need to say, what does it mean to converge? I didn't do this funny arrow. What does it mean for a spectral sequence to converge?
Can you define what is stable processes?
Not off the top of my head. Yeah, no, I have to stay focused. I'll leave this here because it has the things that I wanted to explain. And I'll undo this page. Yeah, so convergence is a really subtle thing. I probably shouldn't spend too much time on it because all of our spectral sequences will have really simple like convergence behavior. But I wouldn't be doing a good job if I didn't mention like the difficulties that arise and what it means to actually converge. So given a graded object H, so it's just something, some algebraic thing, or something that has a grading, okay? And suppose we have a filtration, which is, I'm going to write like 0 contains in, so it'll be a descending filtration that terminates at 0. And it has a length that's equal to the length of our thing. Okay, so if we have some graded object, like a cohomology groups or something like that, and if we've chosen some filtration of it, we say that the spectral sequence converges to it. If, for all n, so the idea is that when we reach the E infinity page, say we look at the things with total degree n, okay? So total degree n. So in this expression, right, so we have these two coordinates p and q, the bi-degree, and we're putting those together to get the total degree of the cohomology we're trying to compute, right? So let's fix a total degree and look at how p, let p vary along this line, and q is just n minus p. So along this line, this is our E infinity, So on our E infinity page, if we have something at point P and its total degree n, so yeah, let's take n minus p, like I said, this should just be the filtration quotient. So for each of these steps, you can take the bigger thing modulo the smaller thing and get a group or whatever. And what the E infinity page is actually computing for you is all of these quotients. So for example, this is going to be Hn mod F1 Hn. And then down here at the bottom, you're going to get like the full thing, Fn Hn. The smallest filtration. Yeah, so down here is going to be the smallest filtration level, and then up at the top, you're going to get the first filtration quotient. So it's very confusing. It's very confusing. So the idea is that, just to reiterate, convergence doesn't mean that everything you see on this total diagonal line, the total degree is n, it doesn't mean that the sum of those is equal to the thing you're converging to. It means that these are the filtration quotients. You have a filtration in mind that you're trying to basically the filtration is going to be generating for you the spectral sequence anyway. And to say that it converges means that you've actually calculated each of these filtration quotients. But then the difficulty is, how do you go from filtration quotients, so like these things are measuring the jump from each group to the next one, or I guess I'm pointing the wrong way, from the smaller group to the bigger one, but that doesn't mean the bigger one is the direct sum of those two things. It can be some non-trivial extension. So you'll hear this a lot in spectral sequences, extension problems. So how do you go from filtration quotients to the graded object itself? And these are called extension problems. And these can be hard, and I won't talk any more about them. All of our examples don't have extension problems, thankfully. But I would be doing a bad job if I didn't at least mention them. Okay. Okay. So there's convergence. So I should at least say, I have to say something about where does the Serre spectral sequence come from. I'll just say the filtration. Just for time. So I don't have time to be prattling on about this. I haven't even done any examples yet. It's been about an hour. So let's get on with it. Yeah. So basically, I'll refer you to Hatcher. So he has Algebraic Topology, the big online textbook. You can use that for a whole lot of things. And there's a mythical chapter 5, which is like an unedited, not complete stuff. And he talks about spectral sequences there. So I'll refer you to that. I at least should say like what the filtration is. Basically, you start with B, CW complex, path connected. And you take BP is the P skeleton. And then EP, let's say like we have pi from E to B, fibration. EP is just pi inverse of BP. So it's the bundle restricted to the P skeleton. And then you get a filtration on your, you basically write down your E1 page is HP plus Q of this. Is that going to work out? Yeah, don't worry about it. I want to get to actual things. So you write down a filtration. This filtration through the method of exact sequences is probably the cleanest way to generate a spectral sequence. So if this was a talk about deriving spectral sequences, so in like the series about the atoms spectral sequence, I did talk about exact couples. Sorry, exact couples. My bad. These are much different. So exact couples, this idea was Massey. But these are the standard way of generating a spectral sequence. The idea is that you just have like two bigraded R modules and some nice maps between them. So you have like anyway. You have you have an exact couple, and then you derive a new exact couple, and then you keep going and going and going, and that's your spectral sequence. So given the filtered complex, you get an exact couple, you get a spectral sequence. If you plug in the right thing and you do the right moves, then you get the Serre spectral sequence. So that's going to have to be for a different time. Yes?
Is it also derived in the ubiquitous sense?
It's derived in like the, probably. It's like you take a homology, basically. Yeah, okay. Doing that. Okay, so this is kind of cool. We can identify these maps. So the homology, the map induced by the projection to the base space, and the map induced by the inclusion of the fiber. in the Serre spectral sequence. So because H star, or rather, like, let's write it like this, H star of B includes into the bottom row, right? So the Serre spectral sequence, which I wrote over there, I'll write it again now. We're going to see it a lot. Right, so if P is the bottom row, Q is the first column, the cohomology of B lives in this row, right? Here's the cohomology of B on the E2 page. Right, so in my construction, I would have written down the E1 page. The E2 page is the homology of that and is conveniently identified with this thing. So the first cohomology of B lies on the first row. Cohomology of F lives in the first column. And if everything's connected, this is just going to be a Z. Okay, so the point is that the E infinity page, right, I wrote it down over there, but the E infinity page sort of shows you the filtration quotients for the cohomology of the total space. And the cohomology of the total space, yes, I will just write it down so I stop waffling. Where are we going? Yes. Check this out. So this surjects, so once you're on the bottom, all of the differentials coming out are 0. This is the point. All the differentials coming out are 0 if you're on the bottom row. So you're always a kernel, right? Anything on the bottom row is a permanent cycle. And the only question is, are you going to get hit by something at some point? But in either way, this is going to quotient out to get to the bottom E infinity page. Okay, that's only going to quotient out to get to the E infinity page. And I won't spell it out because I spent too much time already. This is essentially a subset of the cohomology of the total space E. Subset. I'm just mumbling. It's a subset of the, or a subgroup of the total space. So you get your map, your projection map can be expressed through the spectral sequence as this composition. And so similarly, the fiber F, say HQ of F, this contains, right, so everything here, it has 0 differentials coming into it, so anything non-zero, it can't possibly be in the image of the differential. Well, the only way to get rid of things is if the differentials aren't 0. So you, at the worst case, you're just going to find a smaller collection of elements, those that actually are permanent cycles, but you'll never do any quotient. So your cohomology of F contains the E infinity page there. Contains the E infinity page, and this E infinity page gets mapped to by HQ of E. So, yeah, the point here is that you can actually find these geometric maps inside of the spectral sequence. And so we'll use that a lot in the actual examples, which are about to start. Okay, so we're 1 hour in. We promised a lot of examples, and this is kind of exactly how I knew it would turn out. We've been forever talking about blah, blah, and now we're actually going to start doing stuff. So. Yeah, I hope so. There's a question.
Yeah, I was going to make a comment that this is sort of reminiscent of, if I remember correctly, how Platon showed like you have to check the wrong.
Yeah.
Like you have to check homology along the one column, and then your drum homology is along the rows, right?
Yeah.
Sort of similar idea, but I guess this is for fiber bundles. Particularly,
yeah, so like there's a different, there are different spectral sequences that do different stuff. Like there's also like an Atiyah-Hirzebruch spectral sequence where like you're going to have the cohomology of the base space, and then in vertical directions you're going to have like your extraordinary cohomology of the fiber, or sorry, of a point. And so I haven't read Botan 2 in a while. I think like theirs was kind of like that type of setup instead. Yeah, because they're trying to show something about like what happens if you change coefficients to R. Yeah, and yeah, I think, yeah, and I remember their presentation of spectral sequences, they also do it by exact couples, I'm pretty sure. So it's very standard, very standard. Yeah, I'll keep cleaning board and then start over there while maybe people have more questions or something. Just to try to get all of that stuff out of our taste buds so we can actually do some calculations.
So I guess I don't understand what you're trying to say.
mean, I didn't do a good job of explaining, so yeah. So the ultimate takeaway is sort of that, you know, these two maps, either from the total space to the base space or from the fiber into the total space, we can compute their effect on cohomology using the Serre spectral sequence, in principle. We can realize these maps by first like taking the base. So for the base space, for example, we can map the base space to the E infinity page by just taking quotients and quotients and quotients. And then by thinking hard about the filtration that I wasn't very careful about, you see that this E infinity component actually sits inside. It's like the smallest filtration or whatever.
I at least see the punchline here.
Yeah. And then there's a different picture for F, everything's slightly different. And it comes down to thinking hard about like what are the filtrations at the two extreme points. So I can't really go too far into it because I didn't explain that very well either. Okay, so without further ado, let's start the first example. I'm going to call this example 1 alpha. So this is the first example that anyone ever does when they're talking about spectral sequences. So maybe can somebody already guess what fibration I'm going to write down to solve this problem? No, no one, no takers? Very close. Hop fibration, I heard hop fibration is very close. What we're going to do is compute the cohomology of CP infinity. And so the hop fibration is like a skeleton, the smallest skeleton of the fibration that we care about, which is by definition, if you haven't seen CP infinity before, you start with the infinite dimensional sphere sitting inside countably infinite dimensional complex space with your favorite inner product on it, and then your unit scalars act on the unit sphere, and the quotient is by definition the complex projective space, CP infinity. And so this is an extremely nice fiber bundle. And yeah, all of these are like definitely CW complexes. Yeah, you don't have to do any theorem. It's like they are. They totally are. And this is a fibration. Ah, yes, yeah.
By Whitehead's theorem, right? And
yeah.
Sorry, I meant to say. Yeah, I misspoke. I meant to say by Whitehead's theorem, and it being a CW complex, C infinity is contractible.
Well, C infinity is easily contractible. Yes.
I keep misspeaking.
Yeah. So what Daniel's saying, for anyone who can't pick it up, is that S infinity, this infinite unit sphere, is actually contractible. And the reason is that it's easy to show that its homotopy groups vanish, because by like cellular approximation, any map from the n sphere into it can be contracted down into the n sphere. But that n sphere is bounded on both sides by two n+1 disks. And so you can null homotope the map from any sphere into this thing. And so since it's a CW complex, that means that it actually is contractible by Whitehead's theorem. And this is a fibration, and so we can do the Serre spectral sequence to it. And that's how we solve this problem. So let's get on with it. So what was our Serre spectral sequence? So our E2 page, PQ. This is HP, the base space, which we don't have yet. We don't know anything about this necessarily. HQ of the circle, and it's converging to HP plus Q of the sphere, which by Daniel's great comment, this is a contractible space, so we know exactly what this is. This is just Z in degree 0. And it's 0 everywhere else. So this is some lazy notation I'm going to do to just say that this is like a graded module concentrated in degree 0, and it's Z in that thing. Okay? So where we're going to is done. We know that the E infinity page is going to be basically just Z in degree 0, 0, and nothing else. That's cool. What else do we know? We know what the cohomology of the circle is. That's also, we can just describe it like something in degree 0, something in degree 1. And I'm going to choose to describe it as an integer polynomial ring on one generator called mu1 modulo mu1 squared. Maybe I write that bigger, people watching at home. So a really funny way of doing it, but it makes sense. Okay, so that's what we know about those pieces, but we don't know a lot about CP infinity. But we do know we had, way back when, we had a long exact sequence for a fibration. If you look at the long exact sequence for this fibration, then holy smokes. S infinity is contractible, so that's 0. And then you go pi k CP infinity. And then weird boundary map, pi k minus 1 circle. And then, hey, this one is 0 again. And so you get an isomorphism. And so since S1 is a KZ1, what does that mean? That means that pi n of KGN is isomorphic to G. Sorry, let's try using different letters. If n is equal to k is equal to n, 0 otherwise. So this is a space called an Eilenberg-MacLane space and is defined by this property. And the theorem is, well, this is a CW complex. The theorem is that there exists a CW complex with this property, and that any other CW complex with this property must be homotopy equivalent. So there's a unique homotopy type satisfying this property in the category of CW complexes. Eilenberg-MacLane. 2 names, space. Okay, anyway. Because this only has one non-zero homotopy group, and it's Z in degree 1, this means that CP infinity also only has one non-zero homotopy group, and it's Z, and because you have this shift here, it happens in degree 2. Okay, so at least we know the homotopy groups of CP infinity right away from this fibration and from what we know about the circle. For the Eilenberg-MacLane spaces? Like, yeah, I wrote 2 things. Yeah, I said out loud, did I say homotopy equivalent, or did I say, I mean, yeah, like it's, the symbol KZN is kind of only really like, it denotes a homotopy type. And so like, as long as you're in that homotopy type, then that's what I mean. Yeah. Although there's like, yeah.
Brackets in a degree and square brackets in a model.
Yeah, no. Sorry about that. No, you're right. There are 2 different, I'm using the bracket in 2 non-compatible ways. But if there's a number in the bracket, if it's an integer, versus if it's an indeterminate. Yeah, good question. Okay, so let's actually get to work. So we can start plugging things in and drawing our E2 page and actually solving an example. Okay, so remember, yes, so, okay. When both are 0, this is Z, and so anything with coefficients Z in degree 0 automatically gives you a Z. Like I said, also, if this is 0, then we just get this coefficient group, and we know that H1 is Z. So in fact, I'm going to write it like this. I'm going to write like a angle bracket mu1 to denote that this is like the free abelian group generated by that indeterminate in that singular group. And then there's a color. Finally get to use colors. And then I want to point out that that's where the cohomology of the circle dies. So we have this like terminator line, and everything above that is 0. And so in particular, this spectral sequence obviously abuts, because any differential longer than, or any differential taller than 1 is just going to be 0. So one thing you can note right away is that dr is 0 if r is bigger than 2. So this means that if anything happens, it's going to happen on the E2 page, okay? Which means that since everything has to go away, other than this kind of canonical Z there, everything has to happen on the E2 page. So E2 page is doing a lot, since E infinity is trivial. Okay, so, but we can start filling a little bit more in. Just sort of setting the stage very, very slowly. I'm sure people would like me to go faster, but it's something you have to like slowly absorb. So since we saw CP infinity has the first homotopy group is in degree 2. It follows, in fact, that the first homology group also is in degree 2. And then you'll have to take my word for it that the first cohomology group is also going to be 0. So you can figure out you're going to get a 0 there because it's simply connected, and a 0 here because it's also just like, yeah, the 0 cohomology group with different coefficients. Nothing's happening there. Okay, now something interesting happens. Like I said, we know that everything has to go away. So we have something here that we know is definitely not 0. This generates a copy of Z, okay? But it has to go away. And the only way that it can happen is on the E2 page. So if we write down look at our D2 differential, right? So right on the E2 page, D2 has to be injective, is what I'm trying to say. D2 has to be injective on the E2 page because there's no non-zero incoming differentials. The only way to get rid of this entire copy of Z is if it doesn't go to 0, right? And so similarly, whatever's here, this is the only differential that has any chance of ever hitting that group. So whatever that is, this has to be surjective onto it. And so since D2 has to be injective and surjective, you get an isomorphism here. This is a copy of Z. So this is sort of the first technique of the spectral sequence, is figuring out that this had to be Z. And so I want to like belabor that because this is like the first principle of spectral sequences. So if you have questions now, then definitely ask.
Like earlier, I didn't quite catch why are we talking about algorithmic kind spaces here? Were you just trying to establish these are CW complexes? Or?
For one thing, I wanted to know that this space is simply connected so that I can fill in a 0 there.
Okay.
And I also want to know this later.
Okay.
Yeah. It was just the convenient time to introduce that terminology. Okay. So again, yeah, I'll go through this argument verbally again. We already had an element here. This group is isomorphic to Z. We know that since what we're computing is contractible, everything has to get cleared out by the E infinity page. By the E3 page, the differentials are too long to have any effect. And so everything has to get cleared out on the E2 page. So like step 1, that's how you set the stage. Then, okay, so we have to clear out this entire thing, so D2 has to be injective. Nothing here is allowed to be in the kernel of D2, because then when you do the homology process, it survives to the next page. So this has to be injective. But then whatever this is, there are no other differentials that could possibly eliminate it. So since everything in here is a cycle, so it also has to get hit fully by the incoming differential. So not only is this differential injective, it's also surjective by virtue of the fact that everything has to get cleared out by the next page. So it's the urgency of everything needs to get cleared out is the reason why this differential is an isomorphism. So we get a copy of Z.
That's a beautiful chain of reasoning.
Thank you. That's good. So in other words, we know that H2 of CP infinity is isomorphic to Z.
Maybe it's worth writing for you as isomorphic to Z.
Yeah, okay, yeah. It's a little not clear. Sure. Just while we're still doing like the first example and it's not a customary thing yet. Okay, so by figuring that out, we know that this has to be isomorphic to that. Okay, but now, right, so, but that's the same as just taking coefficients in H1 of S1, as far as groups are concerned. Because this group is also Z, right? So this was like with Z coefficients, but this is also with Z coefficients because we fixed an identification of this group with Z, right? And so we also know that this is Z, just because that's how coefficients and cohomology work. And so now you see how the process goes. So this, well, first of all, the only possible map to this group is going to be 0. And so since this is not allowed to survive to page 3, it has to be 0. So this has to be 0 as well. Now you play exactly the same game as you did with this, except with this copy of Z. This has to get cleared out. There's nothing non-zero coming in because everything is above the terminator line. So this D2 differential has to be an isomorphism onto a Z there. And you continue. This is just an inductive argument that you can formalize. But what you're finding is you get a copy of z in every even degree and a 0 in every odd degree. So already, without even working, well, after writing all that stuff down first, we didn't have to work at all. And we just, the spectral sequence did it for us. We computed the cohomology of CP infinity. Okay. Maybe you're like, oh, but William, why did we do cohomology? Because you could have just done homology. It doesn't make a difference which way the arrows are going. You get the same result. That's a good question to this imaginary person. So there's a structure that I haven't used yet about cohomology, and that is that it gives you a ring. So there's an extra part of this problem, which is compute the ring structure on this. Part beta, compute H star CP infinity as a ring. So we've done it as a graded group, but not as a ring yet. Okay. And the point is that there's a multiplicative structure that I'll just have to really briefly mention. Multiplicative structure. So if we have a couple of classes, one in degree PQ and another in degree P prime Q prime, then we can multiply them together in a way that essentially applies the cup product in the coefficient groups and the cup product in the base space. And I'll call this cup because it is. And so if you wanted to see that like symbolically, maybe you take a sum over I, phi I, beta I, tensor something like sum j, phi j prime, beta j prime. Then this would just be a big sum ij. And then you would do a cup product for the fiber on phi I and phi prime j, and then cup product, so F, and then cup product for the base space on the betas. That's why I called them phis and beta. So you essentially just do cup product. So the problem is that the sign is bad. The sign isn't quite right. What you actually want is to use the Koszul rule instead of just multiplying them together like that. So you want to define multiplicative structure. So I'll just say it like this: alpha star beta equals negative, or how do I say that? Yeah, I'll just say this pretty much a good product. Okay, I think it'll take me too long to write out correctly what the correct product is and why, but essentially you just add a sign here. In fact, I'll just skip the cup and just add the sign. Okay, so what is the sign? What should the sign be? You're taking this Q and this, of course, I did this wrong. Yes, someone should have told me that I did this wrong. The Q's are the fiber variable, P's are the base variable. So because in this expression you're switching a Q into P prime, you have to add a sign of Q P prime to the negative one. So this is how we're going to define our product, and the reason why we define our product this way is because our differential is actually a differential. At least on the E2 page it is. Okay. Right. So the whole point about choosing the sign very carefully is that the differential would satisfy the Leibniz rule. So this is a hidden aspect of the Serre spectral sequence that I didn't say anything about. It's actually a spectral sequence of algebras. And the remarkable thing is that on the E2 page, the multiplication is actually very, very closely related to the usual standard dot product that you'd naturally get, but you have to introduce a sign in order to make sure that the differential that you get is like a differential in the sense that it satisfies the Leibniz rule. Okay, so the fact that the differential satisfies the Leibniz rule is going to let us compute the rest of this argument. So let's go back to our diagram. We already know what the answer is in terms of the groups, and now we just have to fill in what is the ring structure. Okay, so now let's just let iota equal d2 of mu1. So remember, we picked a mu1. It's like an orientation class for our circle. We had a differential that's an isomorphism onto this group, and so we're choosing iota to be the thing that gets hit by mu1. Okay, so now what's the point? Is that once you have this, multiplicative structure is essentially saying that this group is just this group times this group. So this group is actually generated by iota with coefficient mu1. Okay, well, but we can compute that. And then plus or minus mu d2 iota. But d2 iota, that just falls off the face of the earth. So this extra stuff we get in the Leibniz rule disappears, and we just get iota squared. So this guy, this is also an isomorphism. This is a generator, so this group is generated by iota squared. Okay. So this was the mysterious part, is deducing that, in fact, this group is generated by this product class. But it does follow from like the multiplicative structure and the fact that everything is sort of sufficiently spaced out. There isn't any weird terms coming from like coefficient sequences and stuff like that. Once you know, though, that this group is generated by this class, now we can just apply this formula that we have, that I didn't derive, but we have. And we can compute that this isomorphism takes this generator to iota squared. Therefore, iota squared generates this group. And you can follow the logic then. So this is mu1 iota squared. This goes to iota cubed, dot, dot, dot. So in general, so in general, this group, whatever's up there, is generated by mu1 iota to the n. And it sends this generator onto the generator of this thing, which is going to be iota to the n plus 1. So in fact, the multiplicative structure of the spectral sequence let us compute that this is a, well, it depends on who you ask, polynomial ring in one generator, or maybe a power series ring in one generator called iota that lives in degree 2. Okay. So that's why we did it with the cohomology spectral sequence, is so we can exploit the multiplicative structure to actually like reveal algebraic structure in the rows and columns, and you actually have a really interesting thing happening in this big like two-dimensional algebra with these differentials flying around, helping you to actually compute things and get answers. Okay, so that's example 1. Homology spectral sequence. So CP infinity is actually an abelian group, so you do get a Pontryagin ring structure on your homology groups, so maybe you can get something multiplicative, yeah? This is kind of like, everything's already set up. It's pretty kind of straightforward as long as you already established all that homotopy theory stuff. Okay, other questions? This next one's cool. What do you mean? Could you repeat your question? I didn't hear you.
But if we do homology, can we still get information about other stuff like homology? Other topological data?
So Daniel asked if we're doing like computing cohomology, can we still get other stuff with homology? So that particular question, yes, there's this universal coefficients theorem. That's always a tool that lets you translate back and forth between them. And so we'll use that a bit later, assuming I actually do it on time. And you asked, does it tell you information about other things as well? Yeah, it can. There's an example later where we're going to indirectly deduce stuff through using the Hurewicz theorem. So yeah, you can compute lots of topological invariants, and usually they have things that are non-trivial to say about the other invariants. Just realized. Good. So this should be a 2. Missed that one. Okay. So the next problem is sort of similar but different. So one thing that was interesting about this problem was that where's my thing? Yeah. We had a spectral sequence. We didn't compute the cohomology of the total space in terms of the other two. In fact, we actually knew the total space and one of the other two, and we're able to compute the cohomology of the base space. So that's something that it's a 2 of 3 thing. If you know sufficiently much about 2 of the objects in your fibration, then you can deduce a lot of information about the third one through the spectral sequence. And so the next example is going to be where we know what the base space is, we know what the total space is, and we're aiming for the fiber. And so the example 2 is going to be calculate cohomology of the loop space of the sphere, again, as a ring. Loop space of the 3 spheres. So this was a fun problem that was in the rational homotopy theory course. I had a lot of fun sitting down and figuring this one out.
Does that help you write that as the cohomology of the loop space of the reduced suspension of S2? No?
I mean, it's the same space.
Yeah. But writing, do we have any theorems about reduced suspension?
For computing like loops of suspensions of stuff?
Yeah.
There are some things. There's this, I don't know. I don't want to get into it now. I'm trying to stick to the schedule here. Yeah. A good question though. Okay. So here's an interesting thing. So consider the inclusion of a base point into some space X. Just the inclusion of some base point. And now, let's also call that map X0, sure. And now consider that path homotopy fibrant thing, path space of X0 to X. So what is this? Let's call this pi. What was that, remember? So this is the set of all triples. It's worth it to actually write it out. Set of all triples. One of them is in X0, so that's X0. The other one is a path in X. And the third one is the image of X0 in X. Well, that's just X0. Wait, what am I talking about? No, this is just an element of X, yes. Such that gamma goes from X0 to X. So this path space is just all paths that start at the point X0. So then if you take the fiber of this fibration of X0, you get all paths that start and end at the same point, and that's exactly just the loop space. So you can construct the loop space using this crazy path loop for the fibrant replacement just by taking a constant map and then taking the fibrant replacement of that, and then the homotopy fiber is the loop space. So therefore we get a fibration that looks like loops S3 point or something contractible S3. So this is the fibration that we'll use in our Serre spectral sequence. Every X has such a fibration, relating it to its loop space. And yeah, you can try to see how much of the cohomology of the loop space you can compute given in an arbitrary X, but for me, I'll start with the sphere and see how hard it is first. Okay. So one thing that this tells us with the long exact sequence of the fibration for homotopy groups is that pi 2 of loops S3 is pi 3. Is that the right way? Yes, pi 3 of S3, which I'm going to take as granted is isomorphic to Z. And also that this is going to be simply connected. So we can take that as our starting point for the spectral sequence. So 0, 1, 2, 3. Oh, I guess not 3. That should be a 1. So this is a Z, this is a 0, and I said that this was, sorry, this is the 3 sphere downstairs. This is why you always start every spectral sequence calculation by writing down the terms on the E2 page. So our base space is S3, and our fiber is loops of S3. And we're converging to, again, something contractible. So we're going to have the exact same concerns as we had before. Everything has to go to 0 before we reach the E infinity page. So here's our base space is the sphere. And then our fiber is stretching up in this direction. And like I said, it's simply connected. First homotopy group is Z. So Hurewicz theorem says first homology group is Z. Universal coefficient says the first cohomology group is Z. So it's a bit of a yoga there to get that Z, but it's sort of standard toolkit in topology. Okay, so this is where we're going to start. I don't think we know anything else yet, unless I forget. And we do know that there's a big terminator line here, because the cohomology of the 3 sphere is truncated. Okay. So, like we said, all of this has to get cleared out. And since there's 2 columns of zeros, so these zeros are totally vertical, because you get 0 in the base space, no matter what your coefficients that you change it to. Well, what am I trying to say? Is that correct? Anyway, I've convinced myself of this before. These are definitely towers of zeros. And so any differential that's going to make it across to this thing has to be 3 wide. So the only possible differential that we can get is the D3 differential. So everything's got to happen on the E3 page. Okay? And for the same reason as we had for CP infinity, this has to be an isomorphism, because for these 2 particular groups, there's nothing else that can really happen. So this is also a row of zeros. This is an isomorphism, and so this is also a Z. Okay? So let's start naming our classes, though. So I'm going to call this one mu3, and I'm going to call this one kappa 1 to mu3. Okay. And then, since this term has nothing it could possibly send to 0, that has to be 0. Okay? So then the next one here is another copy of, well, yeah, I think this is the way it goes. I'm pretty sure that, yeah, since this entire column's gone, we're going to get like the same repeated thing. We're just going to get copies of Z in every even degree. And so the question is, okay, well, what's the ring structure? So that was easy to do. So kappa 1 squared is going to be living somewhere up there, but we don't actually know if it's going to be a generator or not. So we can think about the differential applied to kappa 1 squared. And this is going to be equal to, right, D3 kappa 1, kappa 1. Since this is living in an even degree, there's no sign for our differential. And since the product is like graded commutative, and this is in an even degree, things will also commute. So we're actually just going to get 2 times kappa 1. D3 kappa was mu2, mu3. Okay? So this differential, which we know has to be an isomorphism, takes kappa 1 squared to 2 times the generator here. Right? So the generator here is a kappa 1 mu3. So whatever kappa 1 squared is, it goes to 2 times the generator. But this is an isomorphism, so there has to be something that is like half as big as kappa 1 squared. So there's a kappa 2 in whatever this group is, E3, 0, 4, such that kappa 1 squared is actually equal to 2 times kappa 2. And the differential D3 applied to kappa 2 is equal to this generator. Okay, so kind of weird. This was kind of a weird argument that I thought was really cool when I figured it out on the assignment. was that, yeah, so I thought it would just be easy, like whatever the square is going to be the generator, so you just figure out it's the polynomial ring on the whatever. But the fact that when you square it and then map it down, you get something not zero, even though you already know this is an isomorphism. You know, that just lets you find something underneath, something that is like, you can divide this by 2, because its image comes with this factor of 2 built into it. It's really bonkers. So you continue this upward, climbing the chain, and you start to find more numbers. Okay, so then what happens if you go to the next one? What happens if you take d3 of kappa 1 cubed? So this is going to be, use Leibniz rule again. This is the only time I can ever competently use Leibniz rule, is when there's no differentiability to anything. I can just close my eyes and do it. But we know what this is. This was, where would I go? 2 times kappa 1 mu 3. So this is kappa 1 squared mu 3 plus, what did I say? 2 times kappa 1 mu 3. And so this is equal to 3 times kappa 1 mu 3. Okay. Oh, did I do this wrong or something? Let's see here. Uh-oh. Okay. Why did I say that this made sense? Let's see. Oh yeah, this became a square, so this should be squared as well. Yeah, so this kappa 1, so this becomes a kappa 1 mu 3, and then with this kappa 1 becomes a kappa 1 squared. Yeah, so that fixes that expression, but this was not the expression that I was aiming to get. But I think this looks like there's no mistake, right? Okay. That should be fine, but you should be getting factorials though. It shouldn't be 3, it should be 6. What did I do? Was I just always wrong and this is correct? That's the other question. I did get full marks on that assignment, so I think it is factorial, but I can't remember why. All right, I'm going to have to bail. And leave this as an exercise. So exercise. Let's call this coefficient Cn. And then is Cn equal to n, or I'll call it C3 or whatever, or n factorial. I think it's n factorial, but I don't remember how I figured it out.
It's always n factorial.
Why is it n factorial? This is not n factorial.
Yeah. That's what I'm trying to figure out too.
There's your exercise. The outcome, though, if I hadn't butchered this, is loops S3 should be integer polynomials on all of these kappa classes, modulo the relation that kappa 1 to the n is equal to Cn times kappa n. And so the Cn is either n or n factorial. And if it's n factorial, this has a much nicer expression where, in fact, it's a kappa n times kappa m gives you n plus m choose n times kappa n plus m. So I'm pretty sure this is what you're supposed to get. But I'm not sure why the Cn is giving me an n and not an n factorial. So I think I'm just going to have to apologize and move on from that one.
Did you indicate that kappa 1 is 2, right?
Yes. Yeah.
So that one is
Okay.
I don't understand. So you gotta have these kappa ones in the leftmost column, and as you go up, you do kappa 1 and you have kappa 1 squared, right?
Yeah, it's like somewhere in this group. Yeah, you don't know what it is though.
But like, why are we saying there's a kappa 1 squared in there? Is it just like...
Yeah, you're using like the multiplicative structure of the spectral sequence. When you restrict it to the column, you actually get like a subring.
Right.
So the column and the bottom row are both subrings. And so you can use like the cup product from the base space and the cup product and the fiber to like tell you how the algebraic structure of the whole E2 page is playing out.
Okay, so it comes from the cup product structure.
Yeah. So this kappa 1 squared, that cup product is in the cohomology of loops S3. Yeah, and so then I'm trying to apply the differential to that, and you do the Leibniz rule, and you get this. I'm confident that this is correct, but I don't know why I'm getting the wrong thing. I remember the first time I did this example, I got n's, and I'm like, figured out later that no, that was wrong, but I don't know why this seems so correct. Okay. So, there's an aside about this example. So you actually get a map, or just a map. So since CP infinity is a KZ2, maps from X to CP infinity are the same as degree 2 cohomology classes. And the idea is in F, you pull back iota. So Eilenberg-MacLane spaces classify cohomology. This is what they do, one of the things they do, which is really surprising. And so we can take our generator in degree 2, our kappa, we can represent it by a map to CP infinity, and therefore kappa star going from H star CP infinity to H star blah-de-blah. What this is going to do is it's going to send iota to kappa 1. So it's going to send iota to the n, to kappa 1 to the n, which we said was that Cn of kappa n. So you can figure out what this map is going to do. Is this injective? And what this turns out after some work. So this is a rational isomorphism. And like I said, this came from a rational homotopy theory course. So the outcome of doing this is to show that if you take loops S3 and then you rationalize it, then that's a model for your Eilenberg-MacLane space KQ2. So that's kind of bonkers. Am I lying? Yeah. All right. Anyway. Okay, so that's example 2. Now I have to choose what I want to cover. We might not get to stable homotopy theory yet. How much time do I have now? 20 minutes. Okay. Yeah, it would be bad if I didn't mention naturality. Okay. So here's another tool that you can use to help you compute spectral sequences. If you have a spectral sequence that you already understand really well, and you know how to get a map from your like fibration to that fibration. So suppose we have F, E, B is a fibration, and we have F prime, E prime, B prime is another fibration. Suppose we have maps that make these squares commute, FEB, where things like everything is pointed. Okay, so then we get a morphism of spectral sequence. So what does that mean? It means that for each R and P and Q, we get a map from the e-art page to the other page, and they commute with the differentials. So in particular, let's just draw this in drawings, because just staring at the symbols is not going to be enlightening. So here's our domain spectral sequence, P plus blah, Q plus blah. Let's not worry about it. And then we have our other spectral sequence over here for these guys, E prime R, PQ, P plus blah, Q plus blah, prime. And so our maps from these give us maps coming back. So this is going to be F star, and this is going to be induced by B star. And we have our differentials on either page. And so we're going to get these sort of like slanted commutative squares coming from this map of spectral sequences. And this is sort of called comparison. People do this comparison method. And so I'm going to use this to compute something that's like very tangible and very easy to see. And it sort of is like a nice example. It's either this example or like doing a lot of esoteric stuff to compute pi4 of S3. And I think this is like a much more illustrative example of like the basic techniques. All right. Okay, this one's fun. So let's think about circle bundles. Over S2. So what do we know? We always start these by asking ourselves what we know. So we know that the classifying space for principal circle bundles is CP infinity, okay? And we also know that this was KZ2. So therefore, for all CW complexes X, what do we have? We have that maps from X into CP infinity. On one hand, this gives us all of our principal S1 bundles. And on the other hand, this is exactly parametrized by degree 2 cohomology classes for X. Just because CP infinity is both of these things. And both of these things follow from our favorite fibration, right? Because this is a principal bundle and this total space is contractible, this is a classifying space. And because this is a KZ1, this is a KZ2. So it's really neat. So a function here, on one hand, goes to the pullback of the universal bundle. And the function here goes to the pullback of the universal Chern class, or iota, rather. And this is usually referred to as a universal Chern class. So C1 of, I guess, our function f, if you want, or of f star e. Okay, so we're going to use this to say that, okay, well, given an arbitrary circle bundle is classified by some map, right? So let's let E over S2 circle bundle, and then C is going to be an element in the degree 2 cohomology, which we're identifying with Z by choosing our orientation mu2. Pick a map, C from S2, a classifying map to CP infinity, so that the pullback of the iota is C, right? I'm choosing to conflate this notation because the degree 2 cohomology class essentially is a continuous function in this case. Okay, and then we get a map of bundles by definition of pullback. Okay, so here's our base space is S2, and here we have E, here's our fiber, and over here we have our classifying space CP infinity, our classifying map C, our universal bundle S infinity, and our map S1. So it's a bundle map, so it matches up all the fibers. This is our classifying map, and we get a bundle map by the fact that it's a pullback. Okay, so this is our setup. So we compute the spectral sequence for these two things, and I can draw them smaller because these are small spaces. So 0, 1, 2. So this is going to be the two-sphere, cohomology of the two-sphere, and it's a circle bundle, so you only ever have to go up to here, okay? So, all right. So the E2 page for this bundle looks like this. That's great. It actually looks a lot like the E2 page for the universal bundle. Remember the universal bundle that we did way back when, which was totally worth me spelling out in great detail. So this is CP infinity. That's the circle fiber. Okay, so the idea here is the only interesting differential is that one. There's only like so many maps from the integers to itself, right? If we can figure out where one goes along this differential, then we can immediately compute the cohomology of the total space of E by knowing this differential. But just by looking at this situation, we don't actually know anything about this differential. All we know is that this bundle is classified by some map to CP infinity by some number. It's a very convenient number. And so now by this comparison principle, we get bundle maps coming this way. And what's good about this spectral sequence is we already know the differentials in this spectral sequence. Right? So we know this differential. We don't know this differential, but we do have a map coming from this thingy over here. It is. It is the first term class, yeah. Oh, no, yeah, this is,
Wasn't it C1 that?
because I didn't feel like it, I guess. What am I trying to say? We have a circle bundle.
Because now I'm confusing the C's. Yeah.
Yeah, with Turing class. Sure. Call this C1, call the map C, and then we say this. Okay, so now we have maps coming back. Like this. We also have map from here to here and a map from here to here, but I don't want to focus on those. I want to focus on this commuting square because we want to figure out what that differential is. Okay? Since the bundle map essentially just identifies the fibers, this is going to be like the identity map for Z. And, well, this C star takes a generator to C1 times the generator here. So this map is multiplication by C1. That's the trick, is that we know exactly what classifying maps to CP infinity look like. So we know what effect it has on cohomology just by like choosing the Turing class. It multiplies by the first Turing class. So we have this map, and this map, and this map. So now we can just figure out that this map is also multiplication by C. So this map is multiplication by C. Our differential is multiplication by C, okay? So therefore, we get two cases, and then we're done. So the first case is if C is 0, then this map multiplication by C certainly is not injective. I don't think that is good. Okay, so if C is 0, therefore the differential D2 is 0, because D2 is just multiplication by C, which means that nothing happens. When you go to the E3 page, right, if this differential is 0, this Z still stays there, this Z still stays there. So we get that the cohomology of E in this case is just Z in each degree. Okay, so if C is not equal to 0, then it's injective, which means that this entire group only leaves behind the 0 element, because that's the only thing that's in the kernel coming out. Everything coming out of here, right, this is the kernel of the differential coming out, so the image gives you the quotient subspace, right? So this is telling us that, in fact, H2 of E is Z mod CZ, or C1Z, and that H1 of E vanishes. Okay, and oh yeah, notice this. So if C is 0, that means that the circle bundle is trivial. And this is consistent with the product, that E is actually the product S2 cross S1. If C is not 0, it's a non-trivial bundle. And you can compute the second cohomology as just the quotient space, or quotient group Z mod C1E, blah, blah, blah. And H1E is 0. So notice the special case of C1 equals plus or minus 1. And then you get H2 of E is also 0. So H star of E is the same as the cohomology of the 3-sphere because E is the 3-sphere. This is the hop fibration. So I started out, Daniel thought I was going to compute the hop fibration. I didn't, and then I did at the last possible second. So I really like this example. It's very simple. It is a very simple example, but what this example showcases is the way that if you have a bundle classified by some map to a classifying space, it showcases the way that the classifying map determines the topology because it affects the differentials in the Serre spectral sequence. So in this case, it's super, super easy because your classifying maps are just parametrized by a single cohomology group. And for our base space, that cohomology group just gives us Z. And so it's super easy to control what these do on the topology. But if you want a bigger challenge, you can go think of a more difficult group, more difficult than S1, and try to like replicate how do you compute the total space of a principal U4 bundle over bloody blah. And it gets difficult. But yeah, that's a good start. Probably over time, so I stop now.
You have 10 minutes, bro.
I have 10 minutes? Maybe I stop officially and then make some remarks. Okay? Yeah. So let's stop. Yes, thank you for, yes. Yes, thanks. Thanks for coming. Yeah, the one example that I would have done, if I had more time, I should mention at least something about it, is that, yeah, so you can extract more information than just cohomology if you use other technologies in synchronous. So there's an example where you compute pi4 of S3.
I was just about to say that.
Yeah.
As a question.
Yeah, so you can compute higher homotopy groups by using a Whitehead tower as like an iterative inductive thing. That's what I said in the abstract. So the idea is you take S3. You know that pi3 of S3 is Z, right? And so you can make a map to KZ3, which is a pi1 or a pi3 isomorphism. Gives you an isomorphism of pi3. Both have integer cohomology groups or integer homotopy groups. It's pretty easy to just take a map from the sphere over here. Once you've constructed this, actually, then you can do it. Okay, so what's the point is that if this is an isomorphism on pi3, we went through all that song and dance about homotopy fibers to say that you can make a space that naturally sits inside of this long exact sequence. So if this is an isomorphism, if you take the homotopy fiber of, I don't know, what do you call this, rho? Then if you go through the long exact sequence, what you get is that the homotopy groups, let's call it F, pi k of F, map isomorphically onto the homotopy of S3 as long as k is greater than or equal to 4, and pi k of F, pi 3 of F vanishes. So the effect, what you've done by choosing this map to this space whose homotopy is concentrated in 1 degree, by choosing this isomorphism in homotopy in this degree, you kind of take the homotopy fiber, what you do is you peel off that layer of homotopy. So this thing now has 1 less homotopy group. You've peeled off the thing in degree 3, and you have now the first thing's in degree 4. So what this is telling you that is that pi4 of F by Horovich is actually H4 of F. And H4 of F you can compute with the Serre spectral sequence because this is a fibration, for example. You can compute H4 of F using this fibration, or there's a slightly easier one by putting like CP infinity here instead. But this is the technique. You peel off the bottom layer using some map to here and construct the homotopy pullback. You use a spectral sequence to actually get the homology at that new layer, and then by Horovich, that new homology is the same as the homotopy, is the same as the homotopy group of the space you started with. So S3 is not, it has, this is a higher homotopy group, but by peeling away the lower layers, we're allowed to use Horovich on that homotopy fiber that has like much less homotopy, compute this using standard techniques, and then just deduce that this homotopy group was the same as the space who has all of this lower homotopy group as well. It's a little bit like a fun thing. You can just keep pushing it forever, but I don't have time. Anyway, sorry for taking up more of your time. Now if people have questions, I am going to answer them. Okay.
How to visualize geometrically the peeling of the.
Yeah, it's not something that is like geometrically clear, because like the geometry can have like a lot of hidden stuff. Like for example, if you have any simply connected finite CW complex, then it has infinitely many non-zero homotopy groups. But yeah, it's sort of like how I like to think about it is I have a stack of like degrees. How do I want to do this? So like pi k plus 1, pi k plus 2, pi k plus 3. And you have maybe something like your one column is your f, and your one column is your s. Right, and so maybe your S column has like a G1, G2, G3. This would be GK, I guess. GK plus 1, GK plus 2, GK plus 3. And then your F is maybe like you keep GK, GK plus 1, but then you chop off everything below that. So I don't think this answers your question. This is just like a schematic diagram of what we're actually doing. And how like the process of constructing like a Whitehead tower sort of looks. But this is like the way that I'd like to picture it, is like you have this thing, but it's not like a geometrically visualizable stuff. You just have lower homotopy groups and you just like lop them off by some destructive truncation process.
Yeah, okay, that's good. Destructive truncation.
Yeah, like the real truncation is when you make like the Postnikov tower. So there's the dual things, right? Postnikov tower is you add cells to kill the homotopy groups on the way up. So you construct very, very destructively this space whose homotopy groups agree with your space in this degree and lower. And then you take like the inclusion of your space into all those extra cells. Gives you isomorphisms in all of these. And then you take the homotopy fiber of that big inclusion to get the Whitehead tower, the stage of the Whitehead tower where you're agreeing. Yeah, so like, whatever. So if I write like Whitehead here, here's your X, and then Postnikov. Yeah, and so you have like GK minus 1. Yeah, there's a bit of like at the crossover, there can be some weird stuff that happens. I don't think it's exactly as clean cut as this. But yeah.
Yeah, absolutely. Honestly, you should just give a talk on obstruction theory.
Yeah, probably.
Stable homotopy theory, yeah.
Who has the time, man? I tried to give a talk on spectral sequences, and the fellow had too many pages.
But I was wondering if, like, the geometric topology, like in surgery, if we ever